In this video, we're going to learn how to implement the quicksort algorithm in C++. So the quicksort algorithm can be used to sort arrays of values of different types. In this video, we'll use the algorithm to sort an array of int values. The quicksort algorithm is much more efficient than many other commonly taught sorting algorithms, like for example bubble sort. So as a result, the quicksort algorithm is used in many real applications. Let's go over an example of how the algorithm works. Let's imagine that we have an array of ints. And in that array of ints, we'll have, let's say, 6 and 3 and 7 and 5 and 1 and 2 and 4. So the quicksort algorithm is a divide and conquer algorithm. What this means is that the algorithm is going to divide the problem to be solved into smaller and smaller subproblems. So in the case of quicksort, initially the portion of the array that it's sorting is the entire array. But as the algorithm proceeds, it's actually going to be sorting smaller and smaller portions of the array. The first step of the algorithm is to find a special element called the pivot in the portion of the array that's being sorted. Now initially, we're sorting the entire array. And initially, we're going to select the last element in the portion of the array that we're sorting as the pivot. So in this case here, 4 is going to be the initial pivot. Then what we'll do is partition the portion of the array being sorted around the pivot. So all the elements that are less than the pivot are going to come before the pivot. And all the elements that are greater than the pivot are going to come after the pivot. So after the partition, the array is going to look like this. We'll have 3, 1, 2, and then 4, and then 6, 7, and 5. So the elements that are less than 4 now come before 4 in the array, and the elements that are greater than 4 now come after 4 in the array. So the array is much more sorted than it was before. If we sorted these unsorted portions here with 3, 1, 2, and 6, 7, 5, the array would actually be sorted. So what we'll do is apply this same quicksort algorithm to each portion of the array here and here. So when we apply the algorithm to this portion of the array and we select the last element as the pivot, we'll have 2 as the pivot. Then if we partition this portion of the array around the pivot 2, we'll get here 1, 2, and 3. So we'll have 1, 2, and 3. And now this portion of the array is sorted. We could continue to apply the process to this portion of the array over here. And we would select 5 as the pivot because 5 is the last element in that portion of the array. And after partitioning this portion of the array around 5, we would get 5 and then 7 and 6. And then we would select 6 in this portion of the array here as the pivot. And we would partition this portion of the array here, and we would get 6 and 7. So here we'll have 6 and then 7. And now the entire array is sorted. So this is the quicksort algorithm. Let's implement it now in C++. So we'll include a couple libraries to help us out. So we'll include the utility library because this library includes a function called swap that we can use to swap two array elements. We'll also include the C stdlib library and the C time library because these libraries include functions that we'll use to help make a version of the algorithm which uses a randomly selected pivot. So recursive functions are often a good way of implementing divide and conquer algorithms. So in the case of quicksort, we'll also use a recursive function. The function is going to have a void return type. The function is going to be called quicksort recursion, and the function is going to accept the array itself as an argument. So we'll have here int array. And the function will also accept 2 array indexes as arguments. We'll have here int low and int high. And low and high are going to define the portion of the array being sorted. And we'll use this function to implement the quicksort algorithm. Now, if we want to call a function to sort an array, it's going to be more convenient to supply the function with the array and the length of the array as arguments. So what we'll do is make a wrapper function called Quicksort, which is also going to have a void return type. And this function will accept the array and the length of the array as arguments. And this function is going to call Quicksort recursion with the initial low and high indexes. Finally, we'll also declare a function called partition, and the partition function is going to carry out the partition step of the Quicksort algorithm. The function is going to return an int value. It's going to return the index of the pivot after the partition. We'll call the function partition, and the function is going to accept the array as an argument, as well as the low and high indexes of the portion of the array that's being partitioned. Now, in the main function, we can declare and initialize an array. So here we'll have int a is equal to, and we'll have 10, 11, 23, 44, 8, 15, 3, 9, 12, 45, 56, and 45, and 45. So this array has a length of 13, so we'll initialize an int variable length to 13. Then we'll call our Quicksort function, and we'll pass it our array A and the length of the array, which is going to be 13. Then after the array is sorted, we'll output the array elements. So we'll have here for int I is equal to 0, I is less than length, and I++. So I is going to go from 0 up until, but not including 13, and we'll output each array element followed by a space. So we'll have here cout, the element in the array at the index I, followed by a space. Then, when this is all done, we'll also output a couple end lines. So we'll have cout, and end line, and end line. Next, we'll implement the Quicksort wrapper function. So down here, we'll have void and Quicksort with int array and int length. And this function is going to call the Quicksort recursion function. So we'll call Quicksort recursion, and we'll pass the array, and the low index is going to be 0, and the high index is going to be length minus 1. So the idea with the Quicksort recursion function is that it's going to sort the portion of the array between low index and high index. So these two indexes define the portion of the array to be sorted. And initially, we want to sort the entire array using the Quicksort algorithm. So we pass in a low index of 0, which is the first index in the array, and we pass in a high index of length minus 1, which is the last index in the array. Next, we can make the Quicksort recursion function. So down here, we'll have void and Quicksort recursion, and the function will have the array parameter and the low parameter and the high parameter. So this function is going to implement the divide portion of the Quicksort algorithm. It's going to recursively apply the Quicksort algorithm to the left portion and the right portion of the current portion of the array that's being sorted. So the first thing the function will do is call the partition function to partition this portion of the array. So we'll pass this function the array and the low index and the high index. And this function is going to partition this portion of the array around a pivot value. It's going to return the index of that pivot. We'll store that index into an int variable called pivot index. And this pivot index will be used to recursively apply the Quicksort recursion function to the left portion of this portion of the array and the right portion of this portion of the array. So here we'll call Quicksort recursion. And this function call is going to sort the left portion of the current portion of the array that's being sorted, where the pivot index defines where the split between the left portion and the right portion occurs. So we'll call Quicksort recursion, and we'll pass it the array. The low index is going to be low, and the high index is going to be pivot index minus 1. So everything up to, but not including, the pivot index is going to be that left portion of the current portion of the array that's being sorted. And then we'll call Quicksort recursion again to sort the right portion of the current portion of the array that's being sorted. We'll pass it the array, and the low index is going to be pivot index plus 1, and the high index is going to be high, because pivot index plus 1 all the way to the high index is going to be the right portion of this portion of the array that's being sorted. So let's go back to our example for a second. So the quicksort recursion function is implementing the divide aspect of the algorithm, where after we partitioned the portion of the array that we're currently sorting, we want to apply the algorithm to the left portion of that portion of the array and the right portion of that portion of the array. To do that, we need the pivot index, because the pivot index tells us the index of the pivot, which tells us where the split is going to occur. So we then apply the algorithm from the low index of this portion of the array up until, but not including, the pivot index. So the algorithm is going to be applied from this element here to this element here. And then we also apply the algorithm from the pivot index plus 1 up until the high index of the portion of the array that's currently being sorted. So the algorithm would be applied to this portion of the array here. And that's the idea. That's what this function does. Now eventually though, we're going to reach a portion of the array that's so small we can't sort it anymore. So eventually we want this recursion to stop. Now what's going on is that each time this function recursively calls itself, either the high index is getting lower or the low index is getting higher. So eventually it's going to happen that the low index is greater than or equal to the high index. So what we'll do is apply this algorithm only if the low index is less than the high index. If the low index is not less than the high index, then we don't really have a portion of the array to sort. If the low index is equal to the high index, that means we have a single element, and we can't really sort a single element. So what we'll do is only apply this algorithm if the low index is less than the high index. Next, we'll implement the partition function, which will partition the portion of the array being sorted around a pivot. So we'll have here int partition and int array with int low and int high. Now initially, what we're going to do is always use the element at the high index as the pivot value. So we'll declare an int variable called pivot value, and we'll assign to it the value in the array at the high index. Then we'll implement the partition algorithm, which is going to move over the elements that are less than or equal to the pivot over to the left portion of this portion of the array. So first we'll have int I is equal to low, then we'll have a loop with a counter variable j. So we'll have for int j is equal to low, j is less than high, and j++. And inside the loop, we'll check if the element in the array at the index j is less than or equal to the pivot value. If it is, we're going to swap the element in the array at the index I with the element in the array at the index j. And only if this is true are we going to increment I by 1. Then, when this is all done, we're going to swap the element in the array at the index I with the element in the array at the index high. So this is probably the most confusing part of the algorithm. Let's go over it with a specific example. Let's imagine that we have our portion of the array 6, 3, 7, 5, 1, 2, and 4. This means that 4 is going to be our pivot value. So we'll have a pivot value of 4. And I is initially going to be at the index low, and j is also initially going to be at the index low, because I is initially set to low and j is initially set to low. Then in the first iteration of the loop, we'll check to see if the element in the array at the index j is less than or equal to the pivot value. 6 is not less than or equal to 4, so we're not going to swap the elements, and we're not going to increment I either. We are going to increment j though. So j is now going to be here. Then again, we'll check to see if the element in the array at the index j is less than or equal to the pivot value. This time it is, because 3 is less than or equal to 4. So now we do swap the element in the array at the index I with the element in the array at the index j, using that built-in swap function. So this element here at the index I is going to be swapped with this element here at the index j. So we'll have 6 and 3. Then we do increment I by 1. So I is now going to be here. So notice how an element that is less than or equal to the pivot has been moved over to the left portion of this portion of the array. So j is again going to be incremented, and j will now be here. Then we'll check to see if the element in the array at the index j is less than or equal to the pivot value. It's not. 7 is not less than or equal to 4. So all that's going to happen is j is going to be incremented by 1. 5, again, is not less than or equal to the pivot value of 4. So again, j is going to be incremented by 1. Then we'll check to see if the element in the array at the index j is less than or equal to the pivot value. This time it is, because 1 is less than or equal to 4. So we're going to swap the element in the array at the index j with the element in the array at the index I. And so 1 will now be here, and 6 will be here. And we'll increment I by 1. And I is now going to be here. Then j is going to be incremented, and j will be here. We'll check to see if the element in the array at the index j is less than or equal to the pivot value. It is, because 2 is less than or equal to 4. And again, the element in the array at the index j is going to be swapped with the element in the array at the index I. So we'll have 2 here and 7 here. And I will be incremented, and so will j. So we'll have I here and j here. Now j is no longer less than the high index. J is now equal to the high index. So this loop is going to stop. Then, as the last step, we swap the element in the array at the index I with the element at the high index. So we'll have 4 here and 5 here. And we have successfully partitioned this portion of the array around the pivot. So 4 is here, and all the elements that come before 4 are less than or equal to 4, and all the elements that come after 4 are greater than 4. So the last thing to do is return this index, the index of the pivot after the partition. So down here, we're going to return I. And the quicksort recursion function is going to use this index as the pivot index to further apply the algorithm to the left portion and right portion of this portion of the array. So now, if we save, compile, and run the program, we'll get here that the array has been sorted. The array has been sorted in ascending order, from smallest to largest. If we want to sort the array in descending order, all we have to do is change this to greater than or equal to. Then if we save, compile, and run the program, we'll now get that the array is sorted in descending order from largest to smallest. Now always choosing the last element in the portion of the array as the pivot can actually be an inefficient approach. So for example, if we had 1, 2, 3, 4, 5, 6, 7, and then if 7 is chosen as the pivot value, the partition function is not going to perform any swaps because all the elements to the left of 7 are already less than or equal to 7. So 7 is in the right place, and the function is going to return this index as the pivot index. Then the quicksort recursion function is going to select this as the left portion of that portion of the array, and it's going to apply itself to this portion. Then 6 is going to be chosen as the next pivot. And again, the partition function is going to go through these elements, but there's not going to be any work to do. No swaps are going to be performed because all the elements are already in the right place. So the index of 6 is going to be returned as the pivot index. And again, the quicksort recursion function is going to apply itself to this left portion of that portion of the array. And again, 5 is going to be selected as the pivot value. And again, the partition function is going to go through these elements. But again, there's not going to be any work to do because all the elements are in the right place. And this is going to continue. And the issue is, this is a very inefficient way to perform the quicksort algorithm. It's going to lead to what's called n-squared computational complexity, because again and again, the partition function is going over the same elements that it's already gone over, and it's not performing any swaps. And the quicksort recursion function is essentially going through the array one element at a time. So using the last element or the first element as the pivot can lead to bad performance when the array is already sorted. And in practice, that often happens, that quicksort is called with an array that's already sorted. With quicksort, we can achieve what's called n log n computational complexity, which is much more efficient if we select better pivot values that more evenly divide the portion of the array. So for example, imagine we have 1, 2, 3, 4, 5, 6, 7. And imagine that we select 4 as the pivot value. In this case, the partition function is not going to have to perform any swaps because all the elements to the left of 4 are less than or equal to 4, and all the elements to the right of 4 are greater than 4. So the pivot is again in the right place. But now, when the partition function returns this index as the pivot index, the quicksort recursion function is going to more evenly split up this portion of the array. So it's going to call itself with this left portion here and this right portion here. So these portions of the array are now being divided in a much more even way. The dividing and conquering of the problem is happening in a more efficient way. If we select the same middle index as the pivot, at this point, we can see the problem is basically done because we'll have these as the pivots, and then we're going to have portions here made up of only one element. And at that point, the problem is solved, but we've done it with less work overall. So selecting good pivot values can reduce the amount of work to be done. There are different strategies for selecting pivot values. One good simple strategy is to randomly select an element between the low index and the high index as the pivot value. So we'll do that. Up here, we'll declare an int variable called pivot index, and we'll set pivot index to a random integer between the low index and the high index, including the low and high indexes. So we'll call the rand function. The rand function is in the C stdlib library that we included. So the rand function is going to return a random integer in the range of 0 to some very large positive integer. What we want though is a random integer in the range of low to high. So then to get a number in this range, what we'll do is add to low a random integer in the range of 0 to high minus low. Because if low is 4, and let's say high is 8, then high minus low is going to be 8 minus 4. And 8 minus 4 is going to be 4. So what we'll have is low plus a random integer in the range of 0 to 4. And because low is 4, we'll have 4 plus a random integer in the range of 0 to 4. That's going to give us a random integer in the range of 4 to 8. So down here, what we'll have is low plus. And then to give us a random integer in the range of 0 to high minus low, we'll have rand and then modulus, and we'll have high minus low plus 1. So the modulus operator percent is going to give us the remainder of dividing the integer returned by rand by high minus low plus 1. So to see why this is going to give us an integer in the correct range of 0 to high minus low, let's imagine we have a low index of 4 and a high index of 8. In that case, we'll have rand modulus and then high minus low plus 1. So 8 minus 4 plus 1 is going to give us 5. Now, if we take any integer in the range of 0 to some very large positive integer, and we divide that integer by 5, there's only 5 possible remainders. We could have a remainder of 0, or 1, or 2, or 3, or 4. So we're going to get a random integer in the range of 0 to 4, which is exactly the range we wanted. So this will give us a random pivot index in the range of low to high, including low and high. So our partition algorithm is built to work with the pivot value in the high index, but now the pivot value could be at a different index. What we'll do is if the pivot index doesn't happen to equal the high index, then we'll swap whatever's in the pivot index with whatever's in the high index. So if the pivot index doesn't equal the high index, which could happen by random chance, then we'll swap whatever is in the array at the pivot index with whatever is in the array at the high index. And then the rest of the algorithm can work the same way as it did before. The last thing we should do is seed the random number generator. Otherwise, we'll get the same random numbers each time our program runs. So what we'll do is up here in our wrapper function, we'll call the srand function to seed the random number generator. We'll use the current time by calling the time function of the ctime library with the argument null. So the time function is going to return the current time when we pass it the argument null. We'll pass that to the srand function to use it as the seed value. This will ensure our program uses different random numbers each time it runs. So if we save, compile, and run the program, we'll again get the sorted array. But this time, we've used a quicksort algorithm with a more robust pivot selection algorithm. So this is how we can implement the quicksort algorithm in C++. Check out portfoliocourses.com, where we'll help you build a portfolio that will impress employers.